Solving logarithmic and exponential equations. So we know exponential and logarithmic functions are inverses of one another because they reflect over our line of symmetry y equals x. And that goes for every exponential and logarithmic equation with the same base. So for a common logarithm, that means our base is 10. And you see with common log, we don't see that base, and it's an understood base 10 for common log. And to remember that, it's because we have a base 10 number system, and its inverse is the exponential 10 to the x. For natural logarithm, we see that written as ln of x, and that is just logarithm with base e. And e is an irrational constant. We call that Euler's constant. It's approximately 2.718, keeps going forever. And Euler's constant represents natural growth seen in nature. For an example, rabbit populations would grow using this base e. And so those are the two named logarithms we have, but we also have other logarithms just with any base. So whatever the base of the logarithm is, its inverse is the exponential with that same base. And so to solve logarithmic or exponential equations, we have to use the inverse. Kind of like how addition and subtraction are used to undo one another, exponentials and logarithms are used to undo one another. They work the same way. And so the big thing we use for solving these equations is this inverse property, where when we have the base of a logarithm matching the base of the exponential, they undo one another because they're inverses, leaving us with that exponent. Or here, if we have an exponential where we have a logarithm with the same base in the exponent, we're left with this result. So if you don't know this property, go ahead and write it down. And we're also going to use the other properties of logarithms when solving equations. So if you don't remember these properties, pause the video, take a screenshot, write them down, or go back and watch another video reviewing how to use these properties. But this is how we can condense logarithms so that we can then use the inverse property to solve the equation. We're going to work through 10 problems together, and at any point you can pause the video or you can skip to a certain problem you would like. Let's go ahead and start with that first one. So here we're going to solve this logarithmic equation for x. So we have log of 5x minus 2 equals 2. So to approach this problem, we have our logarithm by itself, and we're trying to get this x here. However, we see that x is inside this logarithm, so we need to undo the log to get to that x. And this is where our inverse property comes into play. The inverse of a logarithm is an exponential. Well, what's the base of this logarithm? Because we don't see a base, that's an understood base 10. Okay, so that means the inverse is going to be an exponential with base 10. And so I'm going to write this out, but this is a step we can do in our heads. But we exponentiate both sides of the equation, which just means we're going to make both sides of the equation an exponent with base 10. And because this is common log with base 10, these are inverses, leaving us with 5x minus 2. Okay, well, what is 10 squared? 10 squared is just 100. And now we can solve the equation. We just have 2 steps left. We start by adding 2 to both sides. And then we can divide both sides by 5. Now I'm just going to leave that as a fraction since 102 is not divisible by 5. You could also convert that to a decimal if you want. But that's the solution here, 102 over 5. Our next equation, we have an exponential equation, 3 raised to the power of 5x minus 1 equals 27. Now, there are a couple of ways to approach this problem. You might go ahead and recognize, oh, 27 is just 3 cubed. And if you recognize that, then go ahead and rewrite 27 as 3 cubed. And then when you take log base 3 of both sides, let me write this out. This is a step we can eventually do in our heads. Then we know it's just 5x minus 1 equals 3. Okay, so that is one path we could take here. But if you don't recognize that 27 is just 3 cubed, well then let's approach it by using the inverse property to start. So because we have this exponential by itself, x is trapped in the exponent, we're going to take log base 3 of both sides. The whole reason we're taking log base 3 of both sides is because log base 3 of an exponential with base 3, those are inverses, leaving us with 5x minus 1 equals, and then we can put log base 3 of 27 in our calculator, gives us 3. Okay, so you see how we get to the same step with either approach? Now we just have 2 steps left. We add 1 to both sides, and then we divide both sides by 5. So we're left with 4/5. Again, you could convert that to a decimal if you want. I just prefer fractions. So our solution here is 4/5. Okay, our next problem, we're going to solve this equation. This one looks a little different. We have 2 logarithms, right? So we need to start by actually combining or condensing those logs. So based on our properties of logarithms, when we are subtracting 2 logs to condense, they have to have the same base, and here we're going to divide x by 3. Do we see how when we're subtracting logs with the same base, this is how we condense them? Okay, now that we have this logarithm by itself, we want to solve for x, so we have to think, what's the inverse of logarithm base 5? You guessed it, exponential with base 5. So I'm going to write out this beautiful step we can do in our heads. Okay, so 5 raised to the power of log base 5. Those are inverses, so we're left with x over 3. And 5 squared, we get 25. Now we have one step. How do we undo divide by 3? Multiply by 3. And so our solution is 75. All right, our next problem. We're given an exponential equation, but this one's different. We have an exponential on both the left-hand side and the right-hand side. However, because they have the same base, we're kind of set up for an easy problem. If they had not had the same base, we would need to rewrite them to have the same base, just to make it an easier problem on ourselves. But because they have the same base, we can just take log base 2 of both sides, since the exponentials are by themselves on both sides. Log base 2 of an exponential with base 2 leaves us with x minus 1. Same over here, those are inverses. Okay, and so from here, we can just solve for x. So we're going to subtract x from both sides, and you're probably noticing something. we're left with -1 equals -4. And because that is a false statement, here we have no solution. All right, let's look at our next one. Okay, here we have an equation. It's an exponential equation. We have a base of e. So let's see how to start this. We have our exponential here. We have our exponent here. We're trying to get x, but we cannot solve for this x until we have isolated first this exponential term and then just the exponential without a coefficient other than 1. So our first step is to subtract 5 from both sides. So when we subtract 5 from both sides, we're going to get left with 4e to the 2x equals 7. Okay, now let's get rid of this 4. This is 4 times e to the 2x. So how do we undo multiplication? We use division. So we're going to have 7 divided by 4. Now we have our exponential all by itself. Okay, so we have to ask ourselves, what's the inverse of exponential base e? And if you're thinking natural log, great job. We're going to take the natural log of both sides. Because remember, it's all about equivalence here. What you do to one side of the equation, you must do to the other. And because these are inverses, because this is log base e, our natural logarithm, we're left with 2x equals. And then this is going to give us a decimal. And because I don't want to approximate a decimal, I'm going to leave it as natural log of 7/4. And then our last step, we divide by 2. And this is how I'm going to leave my answer because it is the most accurate answer here. I don't want to have to round a decimal. So here's our answer. Natural log of 7/4 all over 2. All right, we're halfway done. For this next equation, we are going to have to condense our 2 logs and then exponentiate to solve for x. So here, because we're adding 2 logs with the same base, when we condense these, that means we're multiplying x by x minus 5. Notice I put x minus 5 in parentheses because when you're multiplying polynomials, you need to use parentheses. Okay. So let's go ahead and we could either distribute this out or undo the logarithm. So we'll start with the log. What's the inverse of log base 6? That's going to be an exponential with base 6. So I've been writing out the step we do in our heads, but this time I'm not going to write it out. We're raising this side to be the exponent with base 6, meaning we're left with x times x minus 5. And then if we raise this side to be an exponent with base 6, we have to do that to this side. We have to focus on equivalence. So we get 6 raised to the power of 1. All right, now I'm going to distribute. X times x is x squared. X times -5 is -5x. And then 6 to the power of 1 gives us 6. Now, this is a quadratic equation. And to solve quadratics, we could either factor, complete the square, quadratic formula. Here, I'm going to try factoring. So I'm going to set it equal to 0. And then I'm going to ask myself, what adds to give me -5 and what multiplies to give me -6? This is just my little X puzzle. It's an organizer for my thoughts. I go through my factor pairs of -6, checking their sums. And I find that negative 6 times positive 1 gives me negative 6, and negative 6 plus positive 1 gives me negative 5. If you were thinking negative 2 and negative 3, that would give you the correct sum, but not the correct product. So you have to check both. So because those are the two numbers I need, those give me the factors x minus 6 and x plus 1. And by using my zero product property, I get the solutions positive 6 and negative 1. Because we cannot evaluate log at a negative number, our solution is 6. Okay, for our next problem, we have an exponential equation, and this looks a little scary, but we just need to take it one piece at a time. So we're going to start by thinking about what we're solving for and how to isolate that. So we're solving for x, and we know we need to somehow get x minus 1. And to do that, we first need to get the exponential by itself. But before that, we need to get this part of the equation by itself, which means we're going to start by subtracting 4 from both sides. So we're going to be left with 1/2 times 2 to the power of x minus 1. 6 minus 4 gives us 2. Now, how do we undo multiplying by 1/2? I like to think of, to inverse multiplying by a fraction, I like to multiply by its reciprocal. So I'll multiply by 2 over 1. And 2 times 2 over 1 gives me 4. Okay, from here, I'm recognizing that 4 is just 2 squared. And if that's not obvious to you at first, we need to practice recognizing patterns. We want to have the same base if we want to take this approach. But we also, because this doesn't have an exponent other than 1, we could have just started with taking log base 2 of both sides. So it just kind of depends on what you want to do. And either way you work it, you're going to get left with x minus 1 equals 2. Therefore, 3 is our solution. All right, just a few problems left. Here we have a logarithmic equation. We're going to solve for x, so we're going to start by subtracting 3 from both sides, which leaves me with 2 natural log of x equals 4. Now, this is 2 times natural log, so I'm going to divide both sides by 2 to get natural log of x equals 2. And then the inverse of natural log is base e, which leaves me with x equals e squared. And because I don't want to round a decimal, I'm going to leave my answer as just e squared. Problem 9, we're going to solve this equation. And this is kind of like one of the problems we've already done. Because we have the same logarithm on both sides, our first step, and this is something we can do in our head, but I'll write it out for you, is to raise both sides to be the exponents of the base of the log. And because it's natural log, that's log base e. So by raising both sides of the equation to be exponents with base e, it undoes those natural logs. And now we have a quadratic equation. So I'm going to set it equal to 0 and solve for x. So I'm asking myself what adds to give me negative 2 and what multiplies to give me negative 3. So I go through my factor pairs of negative 3 and I find that negative 3 and positive 1 complete my puzzle. which gives me the factors x minus 3 times x plus 1. And so, by using the zero product property, I get that my solutions are 3 and negative 1 for this equation. All right, one more problem. We have an exponential equation here. So we're solving for x, and we're going to start by dividing both sides by 5. So we get 2 to the x equals 48. Now, because we're solving for x, how can we undo an exponential? Log base 2. Remember, the whole reason we've learned about logarithms is to help us solve exponentials. Okay, so our left-hand side, because it's log base 2 with an exponential of base 2, those undo one another, leaving us with x. And because 48 is not 2 raised to a whole number, I don't want to round this to a decimal, so I'm just going to leave my answer as log base 2 of 48.